Hello everyone and welcome to the video covering indeterminate forms and L'Hopital's rule. Our objectives for this particular video are number one, recognize limits that produce indeterminate forms, and number two, apply L'Hopital's rule to evaluate these limits. Now the indeterminate forms that we're going to be working with are going to be the two you are most familiar with right now, which is 0 over 0 and infinity over infinity. But we do have these other indeterminate forms as well that we can that we'll have to go through and modify so that we can apply L'Hopital's rule. So that will be what we'll be looking at in this video. So we'll see the development of L'Hopital's rule and then the use of L'Hopital's rule. To really get to the development of L'Hopital's rule, I want you to recall this fact from chapter 2. And this was one of the forms of the definition of the derivative, that f prime of c was equal to the limit as x approaches c of f of x minus f of c over x minus c. You'll notice the difference quotient there. And this is provided that limit exists. Okay, this part, this definition right here of the derivative is going to be key in terms of our development of L'Hopital's rule. So let's start out with this. We're going to let f of x and g of x be continuous and differentiable functions of x such that, and this part is key, f of c equals g of c equals 0. And so what we want to find is the limit as x approaches c of f of x over g of x. Notice that this right here, that this will give us our indeterminate form, in this case of 0 over 0. And so what I have then is that the limit as x approaches c of f of x over g of x will equal the limit as x approaches c of f of x minus f of c over g of x minus g of c. Remember, f of c and g of c are 0, so really I'm just subtracting 0 at this point. I can also go through, and again, because we're taking the limit as x approaches c but not equal to c, I can go through and I can go and divide or multiply, however you want to look at it. I can divide the numerator and denominator both by x minus c. That is not division by 0 because the limit again is what happens is x approaches c but not equal to c. And so this limit here, the limit as x approaches c of f of x minus f of c over x minus c, all over g of x minus g of c over x minus c. By limit properties, that's going to be the limit of the numerator over the limit of the denominator. But you'll notice there's that definition of the derivative. So I know that this piece right here, this numerator, is f prime of c, and the denominator is g prime of c. And if I go through and rewrite that, I can say, well, that's equal to the limit as x approaches c of f prime of x over g prime of x. And so what I get here is that I have found that the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x. And those of you who have done some stuff with L'Hopital's rule will recognize that at this point. Now let's look at the formal statement of L'Hopital's rule. We're going to let f and g be functions that are differentiable on an open interval ab containing c, except possibly at c itself. And we're going to assume that g prime of x does not equal 0 for all x in the interval from a to b, except possibly again at c itself. If the limit of f of x over g of x as x approaches c produce the indeterminate form 0 over 0, then I know that the limit as x approaches c of f of x over g of x equals the limit as x approaches c over f of f prime of x over g prime of x, provided the limit on the right exists. The thing that you have to keep in mind as well, this also applies when you do the substitution, if you get like an infinity over infinity or a negative infinity over infinity. That negative sign here can go to either the top or the bottom, however you want to apply it. Let's take a look now at a couple examples. These examples will put us into the form of 0 over 0 and infinity over infinity. I think everybody is familiar with those, so I just want to kind of review that. In this case, on this first one, we're taking a look at the limit as x approaches 1 of the natural log of x cubed over x squared minus 1. Now, a lot of times what I do on these, I will simplify this as much as I possibly can. So in this case, I know that 3 by log properties, that 3 can be brought out in front. So that becomes the limit as x approaches 1 of 3 natural log of x over x squared minus 1. Which gives us when I do the substitution, I get 3 times the natural log of 1 over 1 squared minus 1, which is 0 over 0, the indeterminate form. And so because of that, I know that the limit, in this case, the limit as x approaches 1 of 3 ln x over x squared minus 1 is going to be equal to the limit as x approaches 1 of the derivative of the top, which is going to be 3 times the derivative natural log of x is going to be 3 over x all over the derivative of the bottom, which is 2x. And so I take that limit as x approaches 1, and I will get 3 over 2. So in this case, I know the limit as x approaches 1 of natural log of x cubed over x squared minus 1 is equal to 3 over 2. Let's take a look at the next one. In this case, we're taking a limit as x approaches infinity of 3x squared plus 4x plus 2 over 3 plus 5x squared. And again, as x goes to infinity, I'm getting infinities in the top, infinities in the bottom, so I get infinity over infinity. Now, another thing on this one should look kind of familiar to you because you dealt with this in pre-calc as well, where you were looking at, we didn't call it the limit as x went to infinity, but if you recall, this is kind of like looking at a horizontal asymptote. But what we have now, because of this, we can apply L'Hopital's rule. So I know that limit is going to equal the limit as x approaches infinity of the derivative of the top, which will be 6x plus 4 over the derivative of the bottom, which is 10x. And again, that gets us, when I do the substitution, if you will, I will get infinity over infinity. And so I can then apply L'Hopital's rule again. Keep in mind that as long as you're getting the indeterminate form of 0 over 0 and infinity over infinity, you can continuously apply L'Hopital's rule. And so that will become the limit as x approaches infinity. The derivative of the top is 6, and the derivative of the bottom is 10. So I will get, in that case, when I reduce it, I will get 3/5. So in that case, the limit as x approaches infinity of this rational function, 3x squared plus 4x plus 2 over 3 plus 5x squared, is equal to 3/5. And again, you'll also remember back in pre-calc, we talked about finding the horizontal asymptote. And the horizontal asymptote, when you have a rational function like that, this limit as you go off to infinity is equal to the horizontal asymptote. Now let's take a look at what happens when we get a different indeterminate form. In this case, what we're going to be looking at is when we get 0 times infinity. Now the key idea on this, okay, is to remember, and this is kind of going the opposite of what we usually deal with, but that when I take a times b, that is equal to a divided by 1 over b. Or I could look at it as b divided by 1 over a. In other words, multiplying by something is the same as dividing by its reciprocal. And in doing that, when I have a 0 times infinity, if we were taking a limit and b goes off to infinity, then 1 over b would be going to 0. So that would give me 0 over 0 in that case. Okay, so let's take a look at an example here. In this case, what I have is the limit as x approaches 0 from the right of x cubed cotangent of x. Now we're using the 0 from the right because cotangent has a vertical asymptote at 0. Okay, so since we're coming from the right, cotangent is positive, and so what happens here, we're going to get 0 times infinity. So that gives me the limit as x approaches 0 from the right of x cubed over cotangent of x. By this property up here, that will be the same as the limit as x approaches 0 from the right of x cubed over 1 over the cotangent of x, which is the same thing as 1 over the cotangent we know is the tangent of x. So I now have this as the limit as x approaches 0 from the right of x cubed over tan x. And so when I do the do L'Hopital's rule, or when I do the substitution, when I do that substitution on that one, that will give me 0 cubed over the tangent of 0, which is 0 over 0. So that's our indeterminate form. So now, by L'Hopital's rule, I know that this limit here is going to be equal to the limit as x approaches 0 from the right of the derivative of x cubed, which will be 3x squared, over the derivative of tangent, which is secant squared. And so that is going to be, when I plug 0 in, that's going to be 3 times 0 squared over the secant squared of 0. And I know secant of 0 is equal to is the reciprocal of cosine. Cosine of 0 is 1, so secant of 0 is also 1. So that's going to be 3 times 0 over 1. So this limit comes out to be 0. So I know the limit as x approaches in 0 from the right of x cubed times the cotangent of x comes out, that limit is equal to 0. Please note, I've just added another line here in yellow. Please note, though, that some of you are looking at that probably saying, well, wait a second, that came out to be 0. I had 0 times infinity, when that just makes sense that it would be 0. Please keep in mind, a modification of this problem can change the answer significantly. For example, what I did here is I moved the exponent. I made this, instead of x cubed, a 3x cotangent of x. It looks very similar. Process is going to be the same. That will be the limit as x approaches 0 from the right of 3x over tangent of x, which we already know is going to be 0 over 0. So I can apply L'Hopital's rule. Derivative of the top is 3. Derivative of the bottom is secant squared. And remember, it's still the same thing. Secant of 0 is 1. And so secant squared of 1, secant squared of 0 is also going to be 1. So this limit here came out to be 3. So here's an instance where something that was in the form of 0 times infinity came out to have a limit of 3 instead of 0 or infinity. So that's why this is called an indeterminate form. Let's take a look at another example. In this situation here, we're going to be looking at infinity, something in the form of infinity minus infinity. Now, the key idea here is to get a common denominator and combine everything into a single fraction. When you do that, then you're going to have something that will either have a limit when you plug in, when you do the limit as you normally do, or you can apply L'Hopital's rule. So in this situation here, I have the limit as x approaches 0 from the right of 10 over x minus 3 over x squared. And again, we're looking at 0 from the right because we do have, in both cases here, we do have a vertical asymptote at x equals 0. And so on this one, when I plug in, when I go and look at this from 0 from the right, 10 over x is going to be infinity. 3 over x squared will also go to infinity. So I get infinity minus infinity. So I go through and I get the common denominator. In this case, x squared. So that will be 10x over x squared minus 3 over x squared. And so this thing really becomes now the limit as x approaches 0 from the right of 10x minus 3 over x squared. Now, in this case right now, I'm going to go and plug in 0. And so that's going to equal 10 times 0 minus 3 over 0 squared, which is going to be negative 3 over 0. So in this case, that limit does not exist. And so this limit, the limit does not exist. Or you could even look at that as this going off towards negative infinity. So here's an instance where we had infinity minus infinity, and we get something that doesn't exist. Again, it is possible. You can go through and take a look at this and see different modifications that could take place to get where you do have a limit. And you'll see these types of problems, see different versions of this throughout. In some instances right here, you could end up with something where you have to go through and apply L'Hopital's rule multiple times as well. Now let's take a look at what happens when we're dealing with 0 to the 0 or 1 to the infinity. In these situations, the key idea that you want to do on this, it's going to be that we want to use the fact that the natural log of x to the n is n times the natural log of x. In other words, that by taking the natural log, we are able to bring that exponent out in front. So that's what's going to end up happening here. We're going to be able to bring that exponent out in front. And by doing that, by bringing that exponent out in front, it's going to rewrite that problem in the 0 times infinity form, which we already know how to solve. We've dealt with that. But we do have a danger. The danger is that when you have this form here, you must undo the natural log to find the limit of the original problem. You go through and find the limit. You get it in the form of 0 times infinity. You find the limit of that. You have found the limit of the natural log of the problem you're trying to fight. Okay? So you're going to go through, you find that this thing comes out to be, that limit comes out to be something like, that limit equals L. That's an L. Then to undo that, I know to undo the natural log, it's E. So the final answer, the limit of the original problem, would end up being E to the L power. Okay, that's what you have to always remember to do. You have to undo that natural log to finish the problem. Otherwise, it's not going to work. Let's take a look at a couple examples. The first example I have, we're going to take the limit as x approaches 4 from the right of 3 times x minus 4 to the x minus 4 power. So you can see this is in the 0 to the 0 property. Okay, so I'm going to take from this, what we do is we take the natural log. So I have the limit as x approaches 4 from the right of the natural log of 3 times x minus 4 to the x minus 4 power. The x minus 4 gets moved down out in front of the natural log. So I have the limit as x approaches 4 from the right of x minus 4 times the natural log of 3 times x minus 4. Now you'll notice when I go plug in 4 there, that's going to give me 0. I'm using 4 from the right because of the natural log, because I have to have a positive here. And this will end up being 0 inside. And the natural log, as we're actually approaching 0, actually goes towards a negative infinity. And so this will then become, I can rewrite that. So remember how we wanted to rewrite that. I can rewrite that as the limit as x approaches 4 from the right of the natural log of 3 times x minus 4 over 1 over x minus 4. Notice multiplying by x minus 4 is the same as dividing by 1 over x minus 4. And that will give me infinity over and then infinity with that. And so I can apply L'Hopital's rule. L'Hopital's rule says that it's going to be the derivative of the top. Well, the derivative of natural log of 3 times x minus 4, the quantity x minus 4 is going to be 3 over 3 times x minus 4, and those 3's will drop off. And the derivative of 1 over x minus 4, which I can think of as x minus 4 to the negative 1, is going to be negative 1 over x minus 4 squared. So I get this part right here. And now I can reduce that. The 3's drop off. And dividing by x minus 4 squared is the same as multiplying the top by x minus 4 to the second power. And so I lost a negative sign there. This would end up being equal to this here, which is that. And then as I take when I reduce that fraction, this comes out to equal 0. So what I end up with here, now remember, this is the answer. That's the limit of the natural log of 3 times x minus 4 to the x minus 4 power as x approaches 4 from the right. That's not what I'm looking for. I'm looking for the limit up here of 3 times x minus 4 to the x minus 4. So I can say that the limit here as x approaches 4 from the right of 3 times x minus 4 to the x minus 4 power is going to be equal to e to the 0 power, which is 1. take a minute here, look back over those calculations that I have, and see what, make sure you're comfortable with those. And if you have questions, make sure to ask them in class. Let's take a look at another example. This time it's going to be 1 to the infinity power. Now this problem right here, this one, again, it comes out to be 1 to the infinity power. This is a very common one, and if you look down below, you see the answer on this one. But this is the definition that we've always had for the number e. We were always told that e was equal to what happened with 1 plus 1 over x to the x as x got very large. Well, let's take a look at that limit, how this process works. Take the limit as x. So I have this up here, which I see as 1 to the infinity power. I'm going to take the limit as x approaches infinity of the natural log of that. So the x comes out in front. So now I have infinity. And then this right inside is going to be 1 plus 1 over infinity. Well, 1 over infinity is 0. So I'm getting the natural log of 1. So I get infinity times 0 because the natural log of 1 is 0. Using that property that multiplying by something is the same as dividing by its reciprocal, I can say multiplying by x is the same as dividing by 1 over x. So I have this one, and so as I take the limit as x goes to infinity, that gives me 0 over 0. So I now can apply L'Hopital's rule. I take the derivative of my numerator. The derivative of natural log of 1 over natural log of 1 plus 1 over x is going to be 1 over 1 plus 1 over x times the derivative of the inside function, which is negative 1 over x squared. Notice I didn't do any simplification, and I'm not going to. Because the derivative of the bottom is going to be negative 1 over x squared as well. And so what I have at this point is that these drop off completely. And so this problem now becomes just the limit as x approaches infinity of 1 over 1 plus 1 over x, which I know as x goes to infinity, 1 over x goes to 0. So this limit is 1. And again, we have to remember we want to go through and undo the natural log. And I did make a mistake there. I see already this should be an x there, not infinity. But the limit as x approaches infinity of 1 plus 1 over x to the x power would then equal e to the first, which is just e. Again, take a look at those. Make sure you're comfortable with what I have on there. And with that, this does now conclude the video on L'Hopital's rule. It kind of goes through, looks at all the different situations you can have. Please remember to look over these examples again. If you have any questions, make sure to ask them. And also, you will need to make sure you download the Socrative app because we will be doing some exit slips. So with that, I will see you in class and hope everything is going well.